So for our project, we have the paraplegic cooling mechanism. I'm Caitlin.
I'm Ernest.
I'm Trent.
And I'm Vincent.
So for our design, we wanted to create a fan system that would help reduce heat stroke and control the user at an appropriate rate. So for the fan system, we want it to be attachable and adjustable for the user's comfort. From our trials and experiments, we were able to create a working fan system that can help cool the user. However, there is more room for improvement, which we shall go on later in the presentation. So the background for this design is that you've all seen a wheelchair, right? They're very awkward, not very maneuverable, and the people bound in wheelchairs have a much harder time keeping themselves cool, as they can't get in the shade very easily, or don't have as easy access to various refreshments. So we wanted to make a attachable fan system that can help cool them down and reduce the chance of ailments such as heat stroke. So with our design, we also want to make the fan head adjustable, so you can position however you want, so it's to the user's comfort. And we also want to have adjustable fan speeds, so that way, depending on how hot it is, the user is cooled at a more appropriate rate. To that end, we've added in a microcontroller to control the fan speed, so that way, depending on the temperature, the fan speed will automatically change to whatever rate is most desirable. And in order to help give more information to the user, we also attached an LCD in order to read the temperature and time, so that way the user is aware of what's going on around them.
Alright, so this is the system block diagram. Since this is a mechatronics class, this is a mechatronics description of the system. So in the top left, we can see that there was a TMP36 temperature sensor. That basically, how those work is they detect the temperature and give off a voltage according to the temperature that's proportional. That information is then conditioned by the Arduino's analog to digital converter, which is then compared to a series of if-else statements to see whether or not the temperature requires a high fan speed, medium fan speed, or low fan speed. And then the digital control architecture is of course also on the Arduino. The main code is stored in the RAM of the Arduino and is executed by the CPU, which allows the temperature to be read, converted into a digital signal that can be compared to the lines of logic within the code. Then we have the output signal conditioning and interface on the bottom right. So to actually drive the motor, we used an H-bridge, and the input pin on the first channel of the H-bridge is driven by the Arduino's digital pins using pulse width modulation. By using pulse width modulation, we can adjust the amplitude of the signal that's being generated by the Arduino, and that can control what percent of the time, depending on the duty cycle, that the motor will be driven or high. This can be used accordingly to control the velocity of the fan. In addition, we included an LCD display that can be used to display the temperature and the time, as well as a loading sequence while the temperature values are being averaged to create debouncing to increase the stability of the overall system. On the following slide, we have a list of the system components. So we use the Arduino Uno microcontroller, mainly because that's the primary one we use in this class. We all have previous experience coding it. Probably one of the easiest microcontrollers to program on the market. Then for our temperature sensor, we use the TMP36 temperature sensor. It's an excellent low voltage selection. It doesn't really require a capacitor to smooth the analog signal going into the Arduino. Pretty much just works out of the package. Then we have the L293D H-bridge, which is an integrated circuit with 4 channels. We only needed to use one of the channels to drive the motor. The voltage from one of the 9 volts is being driven directly through the H-bridge to provide a maximum amount of current and voltage to the motor. Then we have the LCM1602C LCM module, which is just a LCD that's bundled with Arduino kits. We chose specifically this one because it's small, pretty easy to use, and there is a predefined library available by Arduino that can be used to fairly easily program what would be displayed on this LCD. Then we had a simple TFK280SA22125 6-volt DC motor, which is a actuator that just is a pretty low voltage DC motor. We specifically used this motor mainly because we just needed a low voltage, low current motor, as we didn't produce an extremely high power, high voltage system. We just needed a motor that would fit into the necessary constraints in our design. And then there are two 9-volt batteries that are used to power the design. One of the 9-volt batteries is connected directly to the Arduino to control the electronic components in the system. And then there's an additional 9-volt that is used exclusively just to power the motor. It's connected directly to the voltage in on the H-bridge. And then there is a tactile switch that is attached between the positive terminal of the Arduino and the positive terminal of the 9-volt. So this switch allows us to quickly add or remove power from the system just by hitting the switch.
So next we're going to look at the design of our mechanism. So we wanted to make sure that this is a very adjustable device that it can hook up to many different chairs. So first we looked at making it an adjustable height, and so we used two PVC pipes inside of each other, and there's a pin so that you can adjust to 3 different heights. We also wanted to be able to adjust the fan location, so we used a gooseneck connection so that you can move it backwards or forwards to angle it towards wherever you need it to be, and adjust it so it can come a little bit more in front of the user. To make sure that it was adjustable for different chairs, we used many Velcro straps, as you can see in these pictures, so that you can adjust it from chair to chair. And since the chairs are slightly different makes, it'll be able to be used whichever one you have. It's also portable, which is why we decided to use the two 9-volt batteries so that you can use it on the go, and the batteries are pretty easy to change in and out if you happen to run out of power. It's also weatherproof. We used a plastic case to contain the Arduino and a lot of the wires. So in the future we're looking to make it more weatherproof, but for now we're getting there.
So when it came to the way our system operated, we had to make a couple assumptions that for it to be portable, like mentioned, we needed a very small power supply. So we needed very low power components. And we also assumed that our Arduino our code would control all of the logic of our circuits. Again, our considerations for design was just that we wanted it to be lightweight, compact, and adaptable to any chair. And risk factors, we wanted little to no exposed wires, and make sure that our fan did not pose a risk to the user. So we used a foam fan blade, so it's kind of nerfed and safe. Our results, the system's functional. When we built it in the lab, it worked. When we finally assembled it, it remained working. Basically the way it works, we've got temperature thresholds that are set at 70 and 75 degrees. When our temperatures are below or above these thresholds, the speed of the fan ranges from low to medium to high. Our 9-volt battery was more than enough to provide power for our system, and some of the issues we had when we tried to build or solder all of our wires onto a PCB board, we had some issue with the soldering, and so we had to go with the solderless breadboard and header wires. Additionally, some issues we had, the way we mounted our Arduino, it's hard to access the USB and be able to update or hotfix our code, but we don't have any major bugs or errors, so we don't really need to update it. Conclusions, What we learned from this project, commenting your code is really important in being able to find the bugs and the glitches in your programming. It's also really important to test each component before assembling them. That way you can make sure that the component is working correctly, and you'll be better to be able to interface each component together more easily because you'll understand them. And then keeping a really detailed schematic of your circuit really helps in building and rebuilding your electrical circuit and connecting wires when they come loose. Our project cost was an estimated $125, and that's about it.
So moving into the future, there's some things that we can do to improve this project. One of the first things that we want to do is move the LCD and some of the controls to somewhere that's easier for the user to reach. Right now you can see the LCD display when you're not in the chair, but if you were sitting in the chair it'd be almost impossible to read. We'd also like to move the controls hopefully to the armrest where it's much easier for someone who's in a wheelchair to reach them. Right now they're pretty much at a full arm's reach away. We also want to implement the PCB board. As we said before, we tried to get this implemented and we weren't able to make it work. So going into the future, that would add some durability to our project. We'd also like to increase the weatherproofing. We have some exposed wires in the LCD display, and some of the switches are outside of the case right now. So we'd like to get those inside of the case and all waterproof. We also want to have some stronger and easier to use Velcro straps. These straps actually hold somewhat well, but when you want to move around the gooseneck, they can tend to loosen up, and they're hard to attach to the wheelchair the first time you're doing it. On the programming side, we want to make more fan speeds optional. Right now we only have a low, medium, and high, but we feel like we could integrate some more speeds to make it more comfortable for the user. We'd also like to introduce some manual speed controls so that if the user is uncomfortable with what the fan speed is giving them, they can change it themselves. So now we're going to demo our project. When the project first turns on, it says SJSU 2017 and it shows that it's loading. Then once the temperature sensor has a good reading, it will display the time as well as what temperature it is. Here is a demonstration of what the LCD display shows as it goes through the temperature readings.